varying shadowing sensitivity across the slit. The repair deposition height must be controlled very carefully, being different at different positions across the EUV mask illumination slit. 253. Multilayer reflectivity random variations. Global Foundries and Lawrence Berkeley Labs carried out a Monte Carlo study to simulate the effects of intermixing between thermolybdenum, Mo, and silicon, Si, layers in the multilayer that is used to reflect EUV light from the EUV mask. 254. The results indicated high sensitivity to the atomic scale variations of layer thickness. Such variations could not be detected by wide area reflectivity measurements but would be significant on the scale of the critical dimension, CD. 254. The local variation of reflectivity could be on the order of 10% for a few nm standard deviation. 255. Multilayer damage. Multiple EUV pulses at less than 10 mj/cm2 could accumulate damage to a RU-capped Mo/Si multilayer mirror optic element. 256. The angle of incidence was 16 degrees or 0.28 rads, which is within the range of angles for a 0.33 Na optical system. Pellicles. Production EUV tools need a pellicle to protect the mask from contamination. Pellicles are normally expected to protect the mask from particles during transport, entry into or exit from the exposure chamber, as well as the exposure itself. Without pellicles, particle adders would reduce yield, which has not been an issue for conventional optical lithography with 193 nm light and pellicles. However, for EUV the feasibility of pellicle use is severely challenged, due to the required thinness of the shielding films to prevent excessive EUV absorption. Particle contamination would be prohibitive if pellicles were not stable above 200 W, i.e., the targeted power for manufacturing. 257. Heating of the EUV mask pellicle. Film temperature up to 750 K for 80 W incident power, is a significant concern, due to the resulting deformation and transmission decrease. 258. ASML developed a 70 nm thick polysilicon pellicle membrane, which allows EUV transmission of 82%, however, less than half of the membranes survived expected EUV power levels. 259. SiNX. Pellicle membranes also failed at 82 W equivalent EUV source power levels. 260. At target 250 W levels, the pellicle is expected to reach 686 degrees Celsius, 261, well over the melting point of aluminum. Alternative materials need to allow sufficient transmission as well as maintain mechanical and thermal stability. However, graphite, graphene or other carbon nanomaterials, nanosheets, nanotubes, are damaged by EUV due to the release of electrons, 262, and also too easily etched in the hydrogen cleaning plasma expected to be deployed in EUV scanners. 263. Hydrogen plasmas can also etch silicon as well. 264. 265. A coating helps improve hydrogen resistance, but this reduces transmission and forward/or emissivity, and may also affect mechanical stability, for example, bulging. 266. Wrinkles on pellicles can cause CD non-uniformity due to uneven absorption. This is worse for smaller wrinkles and more coherent illumination, i.e., lower pupil fill. 267. In the absence of pellicles, EUV mask cleanliness would have to be checked before actual product wafers are exposed, using wafer specially prepared for defect inspection. 268. These wafers are inspected after printing for repeating defects indicating a dirty mask, if any are found. the mask must be cleaned and another set of inspection wafers are exposed, repeating the flow until the mask is clean. Any affected product wafers must be reworked. TSMC reported starting limited use of its own pellicle in 2019 and continuing to expand afterwards. 269, and Samsung is planning pellicle introduction in 2022. 270, hydrogen bulging defects. As discussed above, with regard to contamination removal, hydrogen used in recent EUV systems can penetrate into the EUV mask layers. Once trapped, bulge defects were produced. 242. These are essentially the blister defects which arise after a sufficient number of EUV mask exposures in the hydrogen environment. Throughput scaling limits. EUV stochastic issues. Shot noise causing significant variations. Lithography is particularly sensitive to stochastic effects. 271. 272, in a large population of features printed by EUV, although the overwhelming majority are resolved, some suffer complete failure to print, e.g. missing holes or bridging lines. A known significant contribution to this effect is the dose used to print. 273. This is related to shot noise, to be discussed further below. Due to the stochastic variations in arriving photon numbers, some areas designated to print actually fail to reach the threshold to print, leaving unexposed defect regions. The lower part of the resist layer is more susceptible to underexposure, due to absorption in the upper part. 274, some areas may be overexposed, leading to excessive resist loss or cross-linking. The probability of stochastic failure increases exponentially as feature size decreases, and for the same feature size, increasing distance between features also significantly increases the probability. 273, 275, line cuts which are misshapen are a significant issue due to potential arcing and shorting. 276, yield requires detection of stochastic failures down to below 1e12. 273. The tendency to stochastic defects is worse when the image consists of photons from different patterns, such as from a large area pattern. 277, or from defocus over a large pupil fill. 278, 279. Stochastic defects tend to occur where there is stochastic absorber dose variation near the threshold dose. These are indicated by where blue specks tend to collect. Multiple failure modes may exist for the same population. For example, besides bridging of trenches, the lines separating the trenches may be broken. 273. This can be attributed to stochastic resist loss. 271, from secondary electrons. 199, 280. The randomness of the number of secondary electrons is itself a source of stochastic behavior in EUV resist images. 205. Some patterns are more vulnerable to stochastic defects, due to pinching between corners. 281, side lobes. 282, or the gap between spots. 283, 284, the coexistence of stochastically underexposed and overexposed defect regions leads to a loss of dose window at a certain post-edge defect level between the low-dose and high-dose patterning cliffs. 285, 286, 287, 288, hence, the resolution benefit from shorter wavelength is lost. The resist underlayer also plays an important role. 273. This could be due to the secondary electrons generated by the underlayer. 195. Secondary electrons may remove over 10 nm of resist from the exposed edge. 199, 289. The defect level is on the order of 1K/mm 2.290. In 2020, Samsung reported that 5nm layouts had risks for process defects and had started implementing automated check and fixing. 291. Photon shot noise can be linked to stochastic defects through the presence of dose-dependent blur, modeled as Gaussian. 292. 293. Photon shot noise also leads to stochastic edge placement error. 294. 295. 296, which can exceed 1 nm. 297. The error can exceed 2 nm when considering the gap between 2-point spread functions. 298. The photon shot noise is removed to some degree by blurring factors such as secondary electrons or acids in chemically amplified resists, but when too significant the blur also reduces the image contrast at the edge. 299. Since the blur is less than the feature size, the feature still enclosed area can still have fluctuations. 300. It is worse for EUV than DUV wavelengths due to lower photon density at commonliest doses, as well as smaller feature sizes being represented by smaller pixels. 301. Line end position affected by shot noise. The natural variation of EUV photon number can cause the position of the line end to shift. Even with blur taken into account, the final distribution of chemical species is still stochastic. Higher dose helps reduce the stochasticity but leads to larger blur, which can spread the extent of the stochastic fluctuations. 302. Another approach to dealing with stochastic issues is to use directional etching to smooth sidewall edges. 303. The resolution of EUV lithography for the future faces challenges in maintaining throughput, i.e., how many wafers are processed by an EUV tool per day. These challenges arise from smaller fields, additional mirrors, and shot noise. In order to maintain throughput, the power at intermediate focus, if, must be continually increased. With the natural Poisson distribution due to the random arrival and absorption time s of the photons. 304. 305. There is an expected natural dose, photon number, variation of at least several %, 3 sigma, making the exposure process susceptible to stochastic variations. The dose variation leads to a variation of the feature edge position, effectively becoming a blur component. Unlike a hard resolution limit imposed by diffraction, shot noise imposes a softer limit, with the main guideline being the ITRS line width roughness, LWR, spec of 8%, 3s, of line width. 306. Increasing the dose will reduce the shot noise. 307. But this also requires higher source power. A 10 nm wide, 10 nm long assist feature region, at a target non-printing dose of 15 mJ/cm2, with 10% absorption, is defined by just over 100 photons, which leads to a 6s noise of 59%, corresponding to a stochastic dose range of 6 to 24 mJ/cm2, which could affect the printability. A 2017 study by Intel showed that for semi-isolated vias, whose airy disk can be approximated by a Gaussian, the sensitivity of CD to dose was particularly strong, 308, strong enough that a reduction of dose could nonlinearly lead to failure to print the via. The two issues of shot noise and EUV released electrons point out two constraining factors. 1. Keeping dose high enough to reduce shot noise to tolerable levels, but also 2. Avoiding too high a dose due to the increased contribution of EUV released photoelectrons and secondary electrons to the resist exposure process, increasing the edge blur and thereby limiting the resolution. Aside from the resolution impact, higher dose also increases outgassing, 309, and limits throughput, and cross-linking, 310, occurs at very high dose levels. For chemically amplified resists, higher dose exposure also increases line edge roughness due to acid generator decomposition. 311, even with higher absorption at the same dose, EUV has a larger shot noise concern than the RF 193 nm wavelength, mainly because it is applied to thinner resists. 274, wavelength resistive absorbance thickness absorption target dose absorbed photon dose quantum yield, 312, acids /nm2 blur acids /blur 2 RF, 193 nm, car 1.2 /m, 313, 0.08 m9% 30 mJ centimeter 2, 314, 27 photons /nm 20.33910 nm 900 EUV, 13.5 nm, car 5 /m, 315, 0.05 m22% 30 mJ centimeter 2, 316, 4.5 photons /nm 2295 nm 225 EUV, 13.5 nm, metal oxide 20 /m, 315, 0.02 m33% 30 mJ centimeter 2, 316, 7 photons /nm 2n /n /3 nmn /o. As can be seen above, at the target incident dose levels, significantly fewer EUV photons are absorbed in EUV resists compared to AF photons in RF resists. Despite greater transparency of the resist, the incident photon flux is about 14 times larger, 193 /13.5, for the same energy dose per unit area. Quantum yield makes the resist response comparable for chemically amplified resists for both RF and EUV wavelengths, but RF resists also allow larger blur, enabling further smoothing. 312. The resist thickness is limited by transparency as well as resist collapse, 317, and resist strip, 318. Considerations. Due to stochastic considerations, the IRDS 2022 lithography roadmap now acknowledges increasing doses for smaller feature sizes. 319, 320, however, even increasing the dose a factor of the fourth of may not be sufficient to eliminate stochastic defects, while at the same hurting throughput. 284, EUV resolution will likely be compromised by stochastic effects. Smaller pitches will be more adversely affected by photon shot noise and blur, with defects already apparent at 30 nm. 321, 322, ASML indicated 30 nm pitch would not use direct exposure but double patterning. 323, Intel did not use EUV for 30 nm pitch. 324. Current stochastic defect densities have exceeded 1 centimeter 2 at 36 nm pitch. This gets worse for smaller pitches, and entails that EUV exposures should only include sufficiently larger pitches. 325, 326, 327, pupil fill ratio. As pitch decreases, a smaller fraction of pupil, fewer illumination angle, may burst. For pitches less than half wavelength divided by numerical aperture, dipole illumination is necessary. This illumination fills at most a leaf-shaped area at the edge of the pupil. However, due to 3D effects in the EUV mask, 328, smaller pitches require even smaller portions of this leaf shape. Below 20% of the pupil, the throughput and dose stability begin to suffer. 51. Higher numerical aperture allows a higher pupil fill to be used for the same pitch, but depth of focus is significantly reduced. 329. Use with multiple patterning. EUV is anticipated to use double patterning at around 34 nm pitch with 0.3